Welcome you all to the fourth tutorial session. I am Thananka Satia and I will be taking you your class today. So let me share the screen. Okay, fine. Okay, so let us begin the class. Today we will be dealing with problems of related to second law of thermodynamics like heat engine, heat pump, refrigerator, etc. So the first question is: during a cyclic process, a heat engine absorbs 500 joule of heat from a hot reservoir, does work, and eject an amount of 300 joule into the surroundings, that is the cold reservoir. You have to calculate the efficiency of the heat engine. Okay, so in this type of problems of heat engine and heat pump, the first priority is you have to draw the block diagram. Okay, so there will be a source reservoir. So here it is called as the source. Okay, then there will be a sink. This is called your sink. And then the next there will be a heat engine that will be operating here. Okay, so it will extract some amount of heat from the source, it will do some amount of work, and then it will dissipate some amount of heat Q2 to the sink. Okay, so what is given to us? It is given that a heat engine absorbs 500 joule of heat from the hot reservoir. That means Q1 is given to us as 500 joule. 500 joule. And then it is given that it does some amount of work and then ejects an amount of heat, and it releases 300 joule of heat to the surroundings. That is 300 joule of heat it releases. That is here Q2 is given to us. Q2 is given as 300 joule. Okay, so then what is the efficiency? Efficiency is nothing but output divided by input. Okay, so what is the output? Output of the heat engine is nothing but the W, and input it is taking as Q1, it is taking as the input. So we don't know what is W, but from this energy conservation we know that Q1 is basically splitted into W plus Q2. So from here we can get W is nothing but Q1 minus Q2. Okay, so from here we can replace this as Q1 minus Q2 divided by Q1, which will be nothing but 1 minus Q2 divided by Q1. Now we know what is Q2. Our Q2 is 300, so 1 minus 300, and our Q1 is 500. So if you cut this 2, it will be 2 by 5, that is 0.4. Therefore the efficiency is 40%. Okay, so the efficiency of the heat engine is 40%. Okay, let us move to the next question then. Here instead of heat engine we are given a refrigerator. So a refrigerator has a COP. COP is coefficient of performance. Coefficient of performance. coefficient of performance. So what it is given, it is given that a refrigerator has a COP of 3. How much work must be supplied to the refrigerator in order to remove 200 joule of heat from its interior? So what does a refrigerator does? A refrigerator, it maintains some amount of temperature inside whatever you keep the food inside. Okay, so what it has to do, it has to extract heat from a particular thing. So we need to calculate what amount of work it should do in order to remove that amount of heat. Because see, if you have to remove heat, the first priority is that you make two temperature different body. If one temperature T1 is greater than T2, then heat will automatically flow from the body at having T1 temperature to the body with T2 temperature. But suppose you want to remove heat and you are doing some work, that means you will not waste your work unless you want to extract heat from T2 to T1. So that is basically the work of a refrigerator. What it does, basically, it has some body which is at say temperature T2, and say this is at temperature T1. So this is something out of the box. Okay, so and this is my refrigerator. That is the refrigeration cycle, which you will be studying in details when if you will be taking any course of refrigeration. Okay, now this just the cycle got reversed. So Q2 amount of heat will be extracted from this body which is having at a temperature T2, and since T2 is less than T1, so according to second law of thermodynamics, if we want to remove heat from lower body to higher body, we must do some additional amount of work to the system, so that we denote it as WP. Just the sign got reversed. Just like the heat engine, all things are same, just the sign got reversed. You have to move the energy from the cold body to the hot body, and in this case you will be requiring some amount of work. Now uh, that is what we need to calculate. We need to calculate this WP, and what is given to us, it is given that we have to remove 200 joule of heat from its interior. That means from this we have to remove 200 joule. So Q2 is given to us as 200 joule. Now what is coefficient of performance? Again, it is just like the efficiency. What we require for a refrigerator, why we buy a refrigerator? We buy a refrigerator to maintain a constant temperature, to cool something. That means our output, our desired output is this Q2. Then only this will be maintained at a temperature T2. So that's why our desired output by input, this is for refrigerator. Okay, so this is our desired output by input. Now what is our desired output? Our desired output is Q2, and what is our input? Our input is, we are giving input WP. Okay, so now then what we know? We know Q2, we know COP. Okay, so we know COP is equals to 3. We'll just put it and we'll get the value of WP. Okay, so then it will be 3 is equal to we know Q2 is equals to 200, so that will be WP. So this will give us WP is equals to 200 divided by 3 joule. Now if we do this, it will be, I think, 66.67 joule. We are starting with some basic questions, then we'll move on to some advanced levels questions. Okay, so this is what questions of refrigerators will look like. Now the third question is, an inventor claims to have invented a heat engine that develops a thermal efficiency of 80% when operating between two reservoirs 1000 Kelvin and 300 Kelvin. Evaluate his claim. That means an inventor, he has invented some machine, and he told that his machine can give an efficiency of 80% if that machine will be working between 300 Kelvin and 1000 Kelvin. And we have to check whether what he is claiming, is it true or false. Okay, so here first of all we will be giving that eta claimed, that means your efficiency that is claimed, eta claimed is equals to 0.8. okay, now we have to check whether this claiming efficiency is equal or not. So that means we have to calculate the maximum efficiency that is possible for this uh, reservoir, this heat engine. Okay, someone may be trying to join. Okay, so eta claim is given to us. Now we just need to check, whether this claim is true or false. Okay, now we have to calculate then what is the possible maximum efficiency. Okay, so once again, this is some source with temperature T1, this is some sink with temperature T2, and this is my heat engine. Okay, it is extracting some amount of work Q1, doing some work W, and dissipating some heat Q2 to the temperature at that one T2. So T1 is given to us as 1000 Kelvin. Okay, T2 is given to us as 300 Kelvin. Okay, now first we will calculate the efficiency. Okay, now efficiency is what? W divided by Q1. Okay, we have already done this. W is equals to Q1 minus Q2 divided by Q1, and that will be equal to your 1 minus Q2 divided by Q1. Now the problem is that we are not given anything in terms of Q1, Q2, nothing else is given now, but it is saying us to check his claim. So that means we have to check the maximum possible. So if we take all the reversible cases, that means if we consider the maximum possible cases, or we consider the heat engine as a reversible heat engine, that is for Carnot engine, for Carnot engine, or we can say that for reversible heat engine, for reversible heat engine, we will, what we basically know for basically reversible heat engine is Q2 by Q1 is equal to your T2 by T1. That means the ratio of the amount of heat extracted from the two reservoirs is equal to the ratio of the temperature temperatures of the two reservoirs. Okay, so that means in place of Q2 by Q1 for eta reversible, we can write this as 1 minus T2 by T1. Okay, so we know what is T2, 300, and we know what is T1, it is 1000. So basically this will be 700 divided by 1000, that is 0.7. So what is telling us that the, if we consider a reversible case where the Carnot engine, which is the, you can say that a hypothetical situation, or the maximum possible efficiency for a heat engine, if it operates between these two temperatures, is nothing but 0.7. okay, so that means the maximum possible efficiency is 0.7. so now the inventor is claiming us that it will give us 80% efficiency. Therefore the claim of the inventor, is false. Okay, therefore the claim of the inventor is false. So let us move to some difficult, quite a bit difficult level of questions. Next is a heat pump. It is used to maintain a house at a constant temperature of 23 degrees Celsius. The house is losing heat to the outside air through the walls and the windows at a rate of 60,000 kilojoule per hour, while the energy generated within the house from the people, lights, and appliances amounts to 4,000 kilojoule per hour. For a COP of 2.5, determine the required power input to the heat pump. Okay, so what it is happening, that there is a house, say this is a house. Okay, so there is a house and there is a heat pump installed here. If I'm marking this one as my heat pump. Okay, so this heat pump inside this house is continuously supplying continuously supplying heat in order to maintain a constant 23 degrees Celsius. Okay, but the problem is that the heat is also getting lost. Okay, so since heat is getting lost, whatever heat is getting lost in steady state, if you have to maintain a constant 23 degrees Celsius, if some amount of heat is getting lost, okay, then that amount of heat should be compensated by the heat pump. That is the ultimate logic. Okay, so if some amount of heat or is you have to maintain a what you call steady state, in steady state condition, if you have to maintain a constant temperature, then what you have to do, if some amount of heat is getting lost, then this heat pump, it will compensate for that amount of heat energy that is lost. Okay, once again, T1, this is my T2. Now I am drawing this one as the heat pump. Now I'm also drawing the arrows of Q1, of Q2, and then WP. Now you have to identify which one is the house. Okay, so giving you one or 2 minutes if you want to identify. Okay, and if someone can tell me what is which one will be the house, and okay, heat pump I'm showing, that which one will be the house, if you can show me. Okay, okay, so see, the work of the heat pump, that it should constantly provide heat. Okay, from so heat pump is providing heat to which part? To the body with temperature T1. So this will be our house. Okay, now this house, it is this house that is at a temperature of T1, it is losing some amount of heat. Okay, and within that house, say there are people, because for a normal person, even if it sits, it really just 3 kilowatt, okay, amount of heat. So if those people are releasing heat, or say lights and appliances, they are also releasing heat, so that means there is some amount of energy generation or heat energy generation within the house is also there, and at the same time there is some amount of loose amount of heat is also there. So what we have to find out, we have to find out first of all the net heat that is loosed by the house. Okay, so first of all, T1 is given to us as 23 degrees Celsius. Okay, so that will be 23 plus 273, that will be equal to your 296 Kelvin. Okay, then now heat lost through the walls. Okay, what is the amount of heat lost through the walls? It is 60,000 kilojoule per hour. Okay, next, heat generated. Heat generated. So the heat generated is 4000 kilojoule per hour. Okay, so there is some amount of heat generation, there is some amount of heat loss. So what will the work this heat pump will do? Heat pump will do the only part of heat, that is total amount of heat that is getting lost. Okay, so net heat lost through the house is equals to 60,000 minus 4000 kilojoule per hour. Okay, so that will be 56,000 kilojoule per hour. Okay, so what will be this? Basically this will be nothing but your Q1, because this amount of heat should be supplied by our heat pump, then only a constant temperature of 23 degrees Celsius, that is 296 Kelvin, can be maintained. Okay, and remember, it's not saying any reversible or not. Okay, now now what we can do, yeah, so Q1 is given to us, COP is given to us as 2.5. Okay, so before that we can convert this Q1 56,000 kilojoule per hour to kilowatt by subtracting it with 3600. Okay, 560 divided by 36. Okay, so that is 15.55 kilowatt. Okay, so Q1 is given to us, COP is given to us. What we need to find? We need to determine the required power input to the heat pump. Okay, so what is the power input? WP, what we know, COP will be what? Again, output by input. Okay, and then what is output? Our output is Q1, because that is our desired output. And what is our input? Input is WP. Okay, so then what is the WP? Is Q1 by COP. Okay, so 15.55 by 2.5. okay, so your COP is 6.22. I'm sorry, it's not COP, sorry, your work required, that's the power input that is required, is power input. Therefore power input is equals to 6.22 kilowatt. Okay, next, an air is okay, so next, an air is contained in a rigid volume at 20 degrees Celsius and 200 kilopascal. A paddle wheel, that is a paddle wheel inserted in the volume, does 720 kilojoule of work on the air. Now if the volume is 2 meter cube, calculate the entropy increase. Okay, calculate the entropy increase. What it is telling, so it is telling that an air is contained in a rigid volume. So okay, and what do you mean by rigid? Rigid means V equals to constant. Okay, so volume is remaining constant, and it is telling us that at a rigid volume, the initial stage, it was what, T was your 20 degrees Celsius, okay, which will be equal to 293 Kelvin. Okay, your P is given as 200, I'm sorry, 200 kilopascal. Okay, now a pedal wheel, it is inserted and it does 720 kilojoule of work on the air. Then the volume is also given to us, 2 meter cube. Okay, so what we have to calculate, we have to calculate the entropy increase. Okay, so now that pedal wheel that is doing that some amount of work, what it will be doing, that work will be basically, it will be doing that amount of work, that pedal wheel, it will, that work will get converted into your heat. Okay, since it is telling us that the volume is remaining constant, and it will also increase, it will also do the increase in the internal energy of the system. Okay, so if for that, let us first calculate the mass. What is the mass? So because we, for calculating that entropy, we will require the mass. How will we calculate mass? We know from the ideal gas equation. Why we apply the ideal gas equation? Because it is nothing it is mentioned about whether it is real gas, it is only telling us air. So until and unless the gas is mentioned as real, we will take it as an ideal gas. Okay, so PV equals to MRT, and from that your M will be equal to PV divided by RT. Okay, now what is P? P is 200 kilopascal, 200 into 10 to the power 3. Volume is your 2, and R is I think 287 for air, joule per kg Kelvin, and your temperature is given as 293. Okay, what will be the answer? 200 into 2 by 0.2872. Okay, so it is approximately equals to 4.76 kg. So that much amount of, that much mass of air is present in it. Now we also know that for an air, the Cp and Cv values, Cp and Cv values we know. Okay, so Cp values is what, 1001.1 joule per kg Kelvin, and Cv value is what, your 717 joule per kg Kelvin. Now since rigid, it is volume is constant. Now if volume is remaining constant, then what will be the value of Q? Q will be equal to M Cv delta T. Okay, M Cv delta T. Okay, so what is the value of M? M is your 4.76, okay, kg, and your if this one I will put it, then Cv 0.717 if I put in terms of kilojoule, and delta T, it will be what, okay, I don't know what is the final temperature, so let me assume, let the final temperature is equal to T2. Okay, so if the final temperature is T2, then your Q, it will be M Cv delta T, that is final temperature minus initial temperature. Okay, this T is in, I am taking it at Kelvin, it doesn't, okay, I am taking this one as Kelvin. Now then since this Q it is doing, so then by first law of thermodynamics, by first law of thermodynamics, okay, we can write this 720, that amount of work, that pedal work, W is equals to your that is 4.76 into 0.717 into T2 minus 293. How it came? Because okay, this was negative, was given 720 kilojoule. How? Because from first law of thermodynamics we know that Q is equals to your uh, Q is equals to your W plus delta U. Okay, so in this case, okay, I'm sorry, the heat is not given to us. Okay, so I'm sorry, this is not the heat basically. So Q is equals to W plus del U, and since no amount of heat is given, so W will be equal to delta U, negative of, and the work is done on the system, so already a negative minus 720 is already there. And for an a gas, ideal gas, the internal energy change is what? M CV delta T. Okay, from here it came, I'm sorry about this, so from here it is coming. Okay, then if you put it here, you will get the value of T2. Okay, so what it will get actually 720 divided by 4.76 into 0.717. 210.96 is equals to T2 minus 293. So from here you will get T2 is equals to 293 plus 210.96 Kelvin. Okay, 503.96 Kelvin. Okay, now next is what we have. We got T2. Now then what we can write, that change in entropy, okay, delta S, that will be simple, M CV ln T2 by T1. I'm sure you have got this formula where you derive for a constant volume process. Okay, so your M was again 4.76, CV is your 0.717, and your ln T2 is your 503.96, and your T1 is your 293. Okay, put all this in calculator. So your answer will be 1.85 kilojoule per kg Kelvin. This will be your change in entropy. This will be your change in entropy. Okay, next is air in a closed vessel of fixed volume 0.15 meter cube exerts pressure of 12 bar at 250 degrees Celsius. If the vessel is cooled so that the pressure falls to 3.5 bar, determine the final pressure, heat transfer, and the change of entropy. Okay, so once again it is telling air is in a closed vessel and the volume is fixed, that is V equals to 0.15 meter cube. That volume is constant. Okay, now it exerts a pressure of 12 bar. Pressure of 12 bar, air is given, so it will be, we will apply the ideal gas. Okay, ideal gas is contained here, and that is air. So it exerts a pressure P1 of 12 bar. Okay, and T1 is given to us as 250 degrees Celsius. Now if the vessel is cooled such that the pressure falls down to your 3.5 bar, okay, your pressure falls down to 3.5 bar, then you have to calculate the final pressure. uh, Final pressure, actually I am sorry, this is a typo, this should be final temperature. Okay, calculate the final temperature. So we have to calculate T2, then we have to calculate the heat transfer Q. Okay, and also we have to calculate the change of entropy, that is delta S. Okay, so initially now, since this is a constant volume process, so uh, we can write from ideal gas equations P1 V1 by T1 is equals to P2 V2 divided by T2. So V1 and V2 is constant, so what we can write this, T2 is nothing but P2 by P1 times T1. Okay, so what is P2? P2 is 3.5, P1 is 12 times T1. T1 is your 250. Oh, this is degree Celsius, I'm sorry, I should have converted this to Kelvin. 293. Okay, so 250 plus 293 50 plus 293 into, I'm sorry, it should be 273. Okay, so this will be 152.5 Kelvin. Okay, so your final temperature is 152.5 Kelvin. Now next is your heat transfer. Okay, now since this is a constant volume process, okay, and you are transferring some amount of heat, then what will be your heat transfer? Your heat transfer will be Q, that will be equal to M CV T2 minus T1. Okay, that will be a heat transfer. Now what is your heat transfer then? M, okay, then you have to calculate the M is equals to P1 V1 divided by R T1. Okay, so I'll put here P1 is what, 12 bar, that is 12 into 10 to the power 5. V1, what is V1? V1 is your 0.15. V1 R is your 287, and your T1 is your 523. Okay, So your mass is your 1.19 kg. Okay, 1.19 kg is your mass. So I'll put it here, 1.19 times CV 0.717, and your T2 is your 152.5, and T1 is your 523. Okay, so your this will be minus 392.88 kilojoule. Okay, so what do you mean by negative? So it's negative means that the heat is rejected from the system. Okay, so this much amount of heat is rejected from your system. Now let us move to the third part. You have to calculate the entropy change. Okay, so entropy change, delta S for an ideal gas is what? Your M Cp ln T2 by T1 minus R M R ln P2 by P1. Okay, so M is common, I can take it outside. M Cp ln T2 by T1, it's a constant volume, minus R ln P2 by P1. Okay, so your M is 1.19, Cp is your 1001. Let me write this is 1.005 better. Okay, so ln, what is my T2? 152.5. T1 is my 523, minus R is your 0.287, and ln P2 is your 3.5, and that is your 12. Okay, so putting all this, ln divided by 12. 0.353. Okay, so your answer will be minus 1.1107 kilojoule per Kelvin. Okay, this is your answer. Okay, now next is a refrigerator working on a reversible Carnot cycle. requires 0.5 kilowatt of cooling to maintain a temperature of minus 15 degrees Celsius. Determine the following. You have to determine the COP of the refrigerator, then you have to determine the temperature at which heat is rejected, and then the amount of heat that is rejected into the surroundings. Okay, so let us draw the block diagram once again. T2, T1, refrigerator, this is Q2, this is Q1, and this is WP. Okay, so what it is given, that a refrigerator working on reversible Carnot cycle, so it is reversible. Okay, and it requires 0.5 kilowatt per kilowatt of cooling. Okay, so for if Q2 is my 1 kilowatt, then my WP will be what? 0.5 kilowatt. Okay, so for 1 kilowatt cooling, and if for 1 kilowatt cooling, you have to require 0.5 kilowatt of work done, and to maintain a temperature of minus 15 degrees Celsius, that means your T2, it is your minus 15 degrees Celsius. If you convert this to Kelvin, okay, so that will be 258 Kelvin. Okay, so now you have to determine the COP of the refrigerator. So first one, COP, it is what again? Output divided by your input. Okay, so what is the output? Your output is Q2 and your input is WP. Okay, so Q2 is 1 and WP is 0.5, so your COP is basically 2. Okay, next is temperature at which heat is rejected. That means your T1, we have to find out what is T1. Okay, since this is a reversible heat engine, reversible refrigerator, so COP, we can also express this as okay, let me take another slide. COP is basically Q2 by WP. Now this WP, I can write Q2, Q1 minus Q2 from the energy balance, then again Q1 by Q2, sorry, this is basically Q1, COP is, no, it's Q2. Okay, Q1 by Q2 minus 1. Now for reversible, Q1 by Q2 is equals to your T1 divided by T2. Okay, so from here we can write it as 1 divided by T1 by T2 minus 1. So if you do this, you will get 1 divided by T1 minus T2 divided by T2. Okay, so that will be equal to your T2 divided by T1 minus T2. Okay, so we have already calculated COP. Your COP calculated is 2, and if you put the reversible part here, you need to calculate what? You need to calculate T1. You need to calculate T1. So T2 divided by T1 minus T2. So you already know T2. T2 is 258. Put it here, you'll get your answer. 2 is equals to 258 by T1 minus 258. So this will be T1 minus 258 129. So your T1 is 387. Sorry, 387 Kelvin. Okay. Now next is amount of heat rejected to the surroundings per kilowatt of cooling. Amount of heat rejected to the surroundings. You have to find out Q1. Third part, you have to find out Q1. So you know Q2, you know WP. So Q1 is equals to Q2 plus your WP. Okay. So your Q2 is 1 plus 0.5, that is 1.5 kilowatt. Okay. Next is a reversible heat engine is operated between two reservoirs of temperature 600 degrees Celsius and 40 degrees Celsius. And the engine drives a reversible refrigerator which operates between reservoirs at temperatures 40 degrees Celsius and minus 30 degrees Celsius. The heat transferred to the heat engine is 2000 kilojoule, and the net work of the combined engine refrigerator plant is 360 kilojoule. Evaluate the heat transfer to the refrigerant and the net heat transferred to the refrigerant at 40 degrees Celsius. Okay, so let us first draw the block diagram. So this is T1. Okay, there is a heat engine. It does some amount of work. Okay, say work E, and takes Q1 amount of heat, releases Q2 to some source T2. Okay, then this it is what T1 is what given to us as T1 is your 600 degrees Celsius and T2 is your 40 degrees Celsius. Okay, and this heat engine, it is a reversible heat engine. Okay, it is a reversible heat engine. Now next, this what it does, then the engine drives a reversible refrigerator, and that refrigerator operates between 40 degrees Celsius and minus 30 degrees Celsius. That means this T2 reservoir, now it becomes the source for our refrigerator, which is also reversible. Okay, refrigerator which is also our reversible. Okay, now this becomes the source for us. So that is T3, and our T3 is given to us as T3 is minus 30 degrees Celsius. Okay, now this amount of work, some part it is used to run this. Okay, what part we don't know. Okay, let us assume this as WP. Okay, then what it is telling, that the heat transferred to the heat engine is 2000 kilojoule. That means your Q1 is given to us as 2000 kilojoule. Okay, and the net work of the combined heat refrigerator plant is 360 kilojoule. That means this W net that is coming out of this entire plant, that is your 360 kilojoule. Okay, so you have to evaluate the heat transfer to the refrigerant and then the net heat transfer to the 40 degrees Celsius. Q2, if I am naming this as Q3 and this as Q4, I have to evaluate what is Q4. Okay, and what is Q2 plus Q3. Okay, so that means I have to evaluate all other heat, that is Q2 equals to equation and also Q3 equals to, so this one I have to evaluate. Okay, and in both case this is reversible, so this is going to be pretty easy for us, just a bit lengthy calculations. Okay, so first of all we know Q1 from that. Okay, in a heat engine reversible, we can write this one as 1 minus T2 by T1. We already derived this formula. Okay, also eta is equals to your what, we divided by q1. So what we can write this as, we divided by q1 is nothing but 1 minus t2 by t1. Okay, so from here we can calculate we, that will be 1 minus t2 by t1 times q1. Okay, so what is your t1? That is your 873 Kelvin. Okay, and just a minute. Okay, so yeah, so the what we have to do, yeah, 1 minus t2 by t1, and then we have to calculate this w1. Okay, so next we 1 minus t2 by t1 times q1. Okay, so what is your t2? 313 Kelvin, and your this one is 243 Kelvin. Okay, so your we will be equal to 1 minus t2 313 by 873 times q1 is your 2000. Okay, so that will be your 1999.64 kilojoule. Okay, so this much amount of work is done. Now from here we can calculate q2. Okay, we know q1 is equals to q2 plus we. So from here your q2 will be q1 minus we. Okay, so what is q1? 2000 minus 1999.64 kilojoule. So your q2 is 0.36 kilojoule. Okay, now then next for the refrigerator, what we require wp. Okay, so again we know we is equals to, since this we is only getting converted to w net and wp, so we is equals to w net plus your wp. Okay, so from here wp is what, it's nothing but we minus w net. Okay, so what is WE? 1999.64, and your W net is given to us as 2000. W net is given to us as 360. Okay, so that will be 1999.64 minus 360. So this is 1639.64 kilojoule. Okay, so if we know WP, now for a refrigerator, COP is what? Your if reversible. Okay, so it will be T2 by T single, whatever. Okay, so COP of the refrigerator, this will be basically equal to your T2 is here T3 by T2 minus T3. Again, COP, we can also write this one as output by input, and what is my output? My output is Q4 and my input is your WP. Okay, so Q4 I need to calculate, and WP is 1639.64. okay, and your T3 is 243 by 313 minus 243. Okay, so your Q4 is 5 6 91.89 kilojoule. Okay, so this much amount of heat is transferred to the refrigerant. Okay, so this is your heat transferred to the refrigerant. This is your heat transfer to the refrigerant. Next it is telling us evaluate the net heat transfer to the refrigerant and the net heat transfer to the 40 degrees Celsius. Okay, so you have to calculate Q2 plus Q3. So we have all the heats. I think Q2 we have, so from here we can calculate Q3. Okay, Q3 is basically your WP plus Q4. Okay, so your WP is 1639.64 and this is your 5691.889. Okay. 7331.53 kilojoule. So therefore net heat supplied to the 40 degrees Celsius reservoir is equals to Q2 plus Q3 that is 7331.53 plus 0.36. Okay, 7331.89 kilojoule. Okay. Next is, the structure of a house is such that it loses heat at a rate of 5400 kilojoule per degree Celsius difference between the indoors and the outdoors, and the heat pump that requires uh, to a power input, a heat pump that requires a power input of 6 kilowatt is used to maintain this house at a temperature of 21 degrees Celsius. Okay, now determine the lowest temperature for which the heat pump can meet the heating requirements of this house. Okay. So what it is telling, that the structure of the house is such that it loses heat at a rate of this one per degree Celsius difference. Okay, suppose this is the house and this is the surrounding. So if there is a 1 degree Celsius difference between these two, then it will lose a heat of 5400 kilojoule per hour. So what will be your first criteria? So first will be, and is it anything it is given? Okay. Now we have to maintain this house at a 21 degrees Celsius. Okay, we have to maintain this house at 21 degrees Celsius. So what we will be doing, we will be assuming, assume the surrounding temperature is equals to T degree Celsius. Okay, so therefore T degree Celsius. So then what we can write, therefore your delta T will be what? 21 minus T. 21 minus T, it will be degree Celsius or it will be degree Kelvin. 21 minus T degree Kelvin. Okay, now next is what? Yeah, so for that means for delta T, then what will be the heat removed for this Q? It will be your 5400 into 21 minus T kilojoule per hour. Okay, so this one we can write as 5400 divided by 3600 times 21 minus T kilowatt. Okay, 5400 divided by 3600. Okay, so this will be basically 1.5 times 21 minus T kilowatt. Okay, next this is your heat lost by the house. Now this amount of heat, it should be what you call, it should be reimbursed by your heat pump. Okay, so now if this is my heat pump, okay, so my Q1 is basically 1.5 times 21 minus T. Okay, then what is my power input? WP is my basically 6 kilowatt, that is given to us. Okay, that's my power input. Now we have to determine the lowest temperature for which this is possible. Now lowest temperature, we know the efficiency is what? It is basically output divided by input, but in this case it will not be an efficiency, it will be this will be your COP. Okay, so what is your output? Your output is for heat pump, it is basically Q1, and that is your WP. Okay, so Q1 WP we know. Okay, now in order to make this in order to calculate the lowest temperature possible, let us assume that this is a reversible case. Okay, let us assume that this is a reversible case where this is my T1 and this is my T2. Then for reversible heat pump, my COP, basically it becomes T1 divided by T1 minus T2. Okay, now we know that reversible cases are always greater than the irreversible cases, or the lowest one. Okay, so for that, according to Carnot's theory, that a reversible case is always having the highest possible COP, or highest possible efficiency. Okay, so from that we know COP reversible is always greater than your calculated COP. Okay, so your COP reversible is what? T1 divided by T1 minus T2. Okay, and what is your COP? Basically you calculated, it is your Q1 divided by WP. Okay, you just have to put this and you will get your answer. Okay, so what is your T1 COP reversible? So you know your Q1 is your 1.5 times 21 minus T. Okay, and your WP is 6. Okay, then your house, that temperature you have to maintain is 21 degrees Celsius. Okay, that T1 is given to you as 21 plus 273, that is your 294 Kelvin. Okay, so it will be 294 divided by 294 divided by T1 minus. Okay, so now if you solve this, you will basically get this will be in degrees Celsius, it will be 21 minus T. Okay, so it will be 21, this is not equal, this will be less than or equal, this will be less than or equal, this will be less than or equal. So 294 divided by 21 minus T is less than or equal to 1.5 times 21 minus T divided by 6. Okay, so from here you get 21 minus T whole square is less than or equal to 1176. Okay, so then your T should be greater than or equal to, if you solve this, minus 13.29 degrees Celsius. So what is the, therefore the minimum temperature that can be, that is required, is equals to minus 13.29 degree Celsius. Okay, next Next is telling us that a heat source at 800 Kelvin loses 2000 kilojoule of heat to a sink at 500 Kelvin for case 1 and 750 Kelvin. Determine which heat transfer is more reversible. Okay, so this is your case 1. Okay, your case 1 is what? From 800 Kelvin it loses heat of 2000 kilojoule to a sink of 500 Kelvin. Okay, now for here our delta S source is what? Source is basically delta S for reversible cases. This is we will consider all the cases as reversible and then we will compare. Okay, Q equals to T delta S. So from here we can get Q by T. Okay, so what is Q? Q is your 2000. So since this is released, so that will be minus, okay, divided by your 800. Okay, minus 2.5 kilojoule per Kelvin. Okay, then delta S sink, this will be again Q by T. Okay, so but now your Q is added, that will be 2000 divided by your 500. Okay, this will be 4 kilojoule per Kelvin. So therefore delta S universe is equals to delta S source plus delta S surroundings. Okay, so minus 2.5 plus 4, that is equal to your 1.5 kilojoule per Kelvin. Okay, so this is your delta S universe. Now let us same calculate for your the second case. An 800 Kelvin source, it releases 2000 kilojoule of heat to a sink at 750 Kelvin. Okay, so here again delta S source, it will be my minus 2000 divided by 800 and that is equals to minus 2.5 kilojoule per Kelvin. Okay, so then delta S sink, this is what? Your 2000 divided by 750. Okay, this is your 2.6 kilojoule per Kelvin. So therefore delta S universe is equals to minus 2.5 plus 2.6, this will give you 0.1 kilojoule per Kelvin. Okay, now see, if you have to answer which one is more reversible, you have to check which has more entropy increase of the universe. So the more entropy increase of the universe is for the case A, therefore case A actually case B is more reversible. Case B is more reversible. Okay, next, a heat pump, it is used to meet the heating requirements of a house and maintain it at 20 degrees Celsius on a day when the outdoor air temperature drops to 2 degrees Celsius. The house is estimated to lose a heat at the rate of 80,000 kilojoule per hour. If the heat pump under this condition has COP 2.5, determine the power consumed by the heat pump and the rate at which the heat is absorbed from cold outdoor air. Okay, so a heat pump, not waste too much of time here. This is my heat pump. This is my heat pump. Okay, takes q2, takes q1 and wp amount of work. Okay, so a heat pump, it is used to maintain a house at a temperature T1 is equal to your 20 degrees Celsius. Okay, so 20 plus 273, that will be 293 Kelvin. Okay, now on a day when the outdoor air temperature drops to 2 degrees Celsius, okay, so that is your 275 Kelvin. Now the house is estimated to lose a heat at a rate of this much. So the house is losing this amount of heat, the heat pump should supply this much amount of heat. Okay, so that means your Q1 is basically the heat lost by the house, okay, and this heat lost by the house is what, 80,000 kilojoule per hour. Okay, so this one, if you convert into kilowatt, 80,000 divided by 3600, that is 22.22 kilowatt. Okay, now if the heat pump under this condition has COP of 2.5, so the first case you have to answer the power consumed. Okay, so COP is what, once again output divided by input. Okay, so your COP is what, 2.5. What is your output? Your output is Q1 and your input is WP. So we don't know WP. From here WP is basically Q1. Q1 is 22.22 divided by 2.5 kilowatt. Okay, so this will be, it is 8.88 kilowatt. Next question, the rate at which heat is absorbed from the outside cold air. That means you have to find out Q2. So that means you have to find Q2. Okay, Q2. Now from here again we will apply the energy balance. What is the energy balance? Energy balance is nothing but Q2 plus WP is basically your Q1. So therefore Q2 is your Q1 minus WP. Okay, so what is my Q1? Q1 is 22.22 and what is my Q1? My Q1 is basically 8.88. Okay, .13 kilowatt. Okay, now let us come to the last question. A car engine with a power output of 50 kilowatt has a thermal efficiency of 24%. Determine the fuel consumption rate of this car if the fuel has a heating value of 44,000 kilojoule per kg. Okay, so the car engine, it is a power output, so its efficiency is given to us as 24%. Okay, and output power it is given to us as 50 kilowatt. Okay, now next is given that the fuel has a heating value of 44,000 kilowatt. So what will be the input heat? Input heat we have to calculate, and from that we have to calculate the fuel consumption rate. Okay, let us assume the fuel consumption rate is equals to m dot. Okay, so therefore input heat is what? Input heat is equals to m dot times 44,000 kg per second, let us assume this. So 44,000 kilowatt. Okay, so now then efficiency is what? Output divided by your input. Okay, so what is your efficiency? Efficiency is your 0.24, your output is 50, and your input is m dot times 44000. Okay, so from here you get m dot is equals to 50 divided by 0.24 into 44000. Okay, so you answer 50 divided by 0.24, 0.0047 kg per second. Okay, so with this I will be ending my class, but I will be waiting for half an hour if you people have any doubt for today's class you want to discuss. Okay. Okay, so since no one is joining, so let me conclude the class here. Thank you.